This week in 241, we'll be learning about AC circuits. Last week, we essentially looked at how an inductor behaves in the presence of an alternating current. This week, we're going to add greater complexity to our circuits by including more components. We're going to be looking at RLC circuits, which contain a resistor, an inductor, and a capacitor in series with an alternating current running through them. All of these components behave differently from each other in the presence of an alternating current. The capacitor is going to allow the maximum amount of current to flow through it when it is uncharged, and have the highest resistance to the current when it is fully charged. The inductor opposes the change in current, and the resistor opposes the current regardless of whether or not it is changing. Therefore, when we plot the voltages over time, we get a very complex behavior of the voltages of the different components. Given the complex behavior, how can we predict what the voltage will be across each component at a given time? The answer is by using phasors. A phasor diagram works like so. We start by plotting the current, which has an amplitude of I max. This amplitude will be the length of the arrow. The current is alternating, so we multiply the amplitude by a sine wave function, which contains the angular frequency at which the current is alternating. It's standard in phasor diagrams to set the current to start at 0 when t equals 0, so we'll plot the current along the positive x-axis. The resistor opposes the current regardless of how the current changes, so the voltage across the resistor is in phase with the current. This phasor diagram will be for voltages, so let's now say that the red arrow has an amplitude that is equal to the maximum current times the resistance of the resistor. Across the capacitor, the voltage is linearly related to the charge stored, and since there's no charge stored until a later time t, the voltage across the capacitor lags the current. In other words, it is out of phase with the current by negative 90 degrees. The amplitude of this arrow is equal to the amplitude of the current times the capacitive reactance. The capacitive reactance is our analog of the resistance for the capacitor and is equal to 1 over the angular frequency times the capacitance. The voltage across the inductor leads the current by 90 degrees. In other words, it is out of phase with the current by positive 90 degrees. The amplitude of this arrow is equal to the amplitude of the current times the inductive reactance. The inductive reactance is our analog for the resistance for the inductor, which is the angular frequency times the inductance. Okay, now that we have that settled, what does that mean for our waveform plot? The red line is the voltage across the resistor, since it is in between the other two. But on which side does the voltage across the capacitor lie? Well, the voltage across the capacitor lags the voltage across the resistor, since it lags the current by 90 degrees. So its peak must occur at a later point in time than that of the resistor. The peak for the voltage across the inductor, on the other hand, must occur before that of the resistor. There is a simple way to remember which voltage is leading and which one is lagging the current. For this, allow me to introduce you to my friend. This is Eli the Iceman. For this acronym, keep in mind that the letter E is used for EMF, and thus refers to the voltage. So in an inductor, the voltage leads the current. In a capacitor, the current leads the voltage. We can determine the voltage for the entire circuit by using vector addition to add all the voltages together. Using this method, we can determine the amplitude and the phase angle. The effective resistance of the circuit as a whole is known as the impedance. Using the Pythagorean theorem, we can determine what the value of the impedance must be. The resonant frequency of the circuit is when the current is flowing with the least resistance. Therefore, this occurs when the effective resistance of the circuit is at a minimum. In other words, when the impedance is a minimum. Looking at the equation, it is clear that this will happen when the difference between the inductive reactance and the capacitive reactance is 0. That is, when the two are equal. Using algebra, we can calculate the value of the resonant frequency. To summarize everything in one place, here's a table of the different components, their Ohm's law and resistance analogs, as well as the phase angle between the components and the current. Because this is the last lab, this will be the last lab video for the class. Eli and I would like to wish you good luck on your finals and hope you have a wonderful summer.